I'm going to present a literature review of nanoparticles applied in medicine. This is an sorry.
That's okay. All right, there you go.
Okay. So here is a little bit of the overview of the topics that I will going to discuss. First, like some introduction of nanotechnology, then some types of nanoparticles and classification, then quantum dots of gold nanoparticles in medical applications, and also some important properties I will going to discuss, and finally the toxicity and challenges, and the conclusion. So first, what are nanoparticles and why nanotechnology? First, why nanotechnology? Well, in 1960, Richard Feynman did a lecture that its name was "There's a Plenty of Room at Bottom." In this lecture, he discussed that it was possible to technically possible to manipulate atomic matter at atomic and molecular scale. This nanotechnology now is an applied science that has rapidly grown, and with the advent of this nanotechnology, the prospect for using these engineering materials in medical application has also grown. So in figure number 2, you can see different types of nanoparticles. But what is a nanoparticle? Nanoparticles are defined as engineering structures with diameters with less than 100 nanometers, are also devices and systems produced by chemical and physical processes having specific properties not necessarily displayed in the macroscale counterpart. But now, what applications could be in medicine? But nanotechnology can be used in a variety of medical applications, especially when combined with antigen-specific coatings or functional groups on their surfaces. The therapeutic and diagnostic usefulness of inorganic nanoparticles depend on many properties, but mainly on their size, physical properties, or chemical compositions. Also, they must be small enough to circulate through the bloodstream and tissues without becoming lodged in capillaries or other microanatomies. Nanomedicine, it's a frequently term that you can find in different papers, so I thought that it was important to put here the definition. The nanomedicine is the application of nanotechnology in the diagnosis, monitoring, and control of diseases at a molecular level using engineered nanodevices and nanostructures. You could classify nanoparticles by the material. So we have metallic nanoparticles, semiconductor, and polymeric. Here I will discuss only quantum dots and gold nanoshells. There are semiconductor and metallic. But here, first, this is the first nanoparticle that I will going to discuss. But what are quantum dots? These nanoparticles are fluorescent semiconductor nanocrystals with these unique photophysical properties. They are composed of materials from the elements in the periodic table groups of the second and sixth, or third and fifth groups. As for example, you can see this in this blue in circle, like cadmium telluride in the periodic table or cadmium selenide. The general structure of a quantum dot consists in an inorganic core semiconductor material like the one that I said before, cadmium telluride or cadmium selenide. But also, this is further coated with an organic aqueous coating, which biomolecules can be conjugated. For example, those you see at the presentation. For example, antibodies, oligonucleotides, peptides. These outer shells protect the quantum dot from photochemical damage and increase their water solubility. The choice of the shell and coating is important as the shell stabilizes the nanocrystal core and also alters the photophysical properties. The outer shell protects the quantum dot from photochemical damage, as I said before. Important properties also of quantum dot is that their core is toxic, reactive, and unstable, and prone to chemical degradations. That's why, as I said, covering it with another semiconductor material, with a higher band gap, for example this zinc sulfide, could improve and increase their stability and quantum yield, but also passivate the toxicity of the core by itself. What is the physics of quantum dots? So to understand this, we must review some atomic structures of semiconductor materials in general. So in the bulk form, the electrons exist in different range of energy levels. There are two types of energy levels separated by this band gap, this region that is called band gap. So the electrons occupying the energy levels that are above the band gap could be classified as the conduction band, and those below is the above is the conduction, yes, and above this the valence band. So, but for an electron to jump from a valence band to the conduction bands, it must acquire some extra energy to cross that band gap. As you see in the image figure 7, you can see at the left part an incident light that is the source. Applying a stimulus such as heat or laser can stimulate the electrons to jump to the conduction band. So as the valence electron jumps above, it leaves behind an positively charged hole. The valence electrons stays in the conduction band only temporarily before falling back to their corresponding valence position or initial position. This electromagnetic radiation emitted as the electron falls back is of different wavelength from that one of the stimulus that you see. The one at the right of the image of figure 7 and the one at the left have different wavelengths, as for example. So you could see in this image different, like a GIF of different types of quantum dots that change the size of the quantum dot by changing the color or radiation that it emits. Important fact is that a band gap determines this emission frequency of a quantum dot, so it's possible to control the color output by altering the size of the quantum dot with extreme precision, as you see in that image. So now, what are the medical applications of these quantum dots? I'm going to discuss here two applications. The first one is imaging and diagnosis. It's important to know that molecular imaging is a great discipline in medicine and biology. You can detect, quantify, and display molecular and cellular changes that happen in vitro and also in vivo. Currently, we have traditional dyes as organic dyes, but they have some limitations. So quantum dots come here to improve those techniques because, as I said before, they have these unique properties that make them an excellent candidate for multiplex assays, enabled to simultaneous probing of different molecules and cells, labeling quantum dots with different colors at the same time and using only a single excitation source, saying that it wasn't possible with the organic dyes. The bioconjugation is made to target specific tissues and can be used as a fluorescent probes. In figure number 8, you can see a cell and different types of the structure of the cell at the same time with only one excitation or one source. In figure number 9, you can see the fluorescent photostability and fluorescence intensity of quantum dots compared with the organic dye that in this case is Alexa, its name. So for an image from A to E, or you can see in general an evolution over time with different organic or different dyes. For example, red one is the quantum dot and the green one is the organic dye. So we can see that, for example, at 3 minutes, the only brightness is due to the quantum dot. The organic dye has reduced its brightness, so quantum dots are good fluorescent. They have a good photostability. Also, quantum dots could be used for medical applications such as imaging, but in cancer. Sorry, that the word cancer, it's not clear, but it means cancer. So now, currently, there are some imaging techniques, traditional techniques to screening cancer, but there are some limitations. Like, for example, it's not sufficiently sensitive to detect small numbers of malignant cells in the primary or metastatic sites. So the idea is that quantum dots could improve those techniques and develop new imaging with high sensitivity and biospecificity. They are not currently applied in clinic. They are on the early stage, but they could be in the future a great material or to fulfill this requirement for in vivo cancer imaging. In this image, I did of some of the literatures that I read a comparison between fluorophores, traditional fluorophores, and quantum dots. The important one are the emission spectrum that in traditional organic dyes or fluorophores it's broad, but in quantum dots it's narrow. You could change it by changing the size of the particle. Also, we have the photostability, as we saw in figure number 9 before. We saw that quantum dots are better in photostability. Also, the spectral multiplexing is ideal in quantum dots, but it's possible in traditional organic, but it's ideal in quantum dots. But there are also some properties that are not so good. For example, the toxicity and clinical applications. In quantum dots, it's little known yet. It's under study that this toxicity that could emit this heavy metal leakage of the cores. Meanwhile, in traditional organic fluorophore, it's variable. It depends on the type of the dye that you have. But the clinical applications are they are currently in traditional organic fluorophores, but in quantum dots are under analysis. The second application of quantum dots in medicine, it could be the use as a photosensitizer in PDT. PDT is a photodynamic therapy, and that is a new form, or it's just like a cancer therapy that is not invasive. And how does it works? Well, it involves an external light source activation of the specific kind of chemicals called photosensitizers that are drugs that generate this reactive oxygen species, like for example this singlet oxygen that is cytotoxic reactive and that causes the destruction of the cancer cells. So what is the role here of quantum dots? The idea is that quantum dots could do two things: to sensitize the PDT photosensitizers through FRET mechanisms, or to interact directly with molecular oxygen to generate this reactive oxygen, reactive species, to let this apoptosis of cancer cells. There are some problems now of traditional methods. For example, it has limitation due to low water solubility. So quantum dots idea is that, as I said, they have a lot of good properties, but they could reduce those side effects and improve that efficiency. This is in figure 11. You can see some of the steps of the procedure of PDT, the traditional method of PDT. The final nanoparticle that I will going to talk is the gold nanoshells. But gold nanoshells are spherical particles with diameter typical ranging from sizes from 10 to 200 nanometers. They are composed of a dielectric core, as you see in figure 13, with also covered by a thin gold shell. And the synthesis or the fabrication of these gold nanoshells, it's made by a growth of this gold colloid, and you can see in figure 12 that is a transmission electron microscopy image. But something important to say, it's the main application, the main property for the medical application is the surface plasmon resonance, which consists in a resonance that arises from the collective oscillation of the conduction electrons in the gold shell, with efficiently coupled to the incident electromagnetic field and propagates through the surface. You can see in figure 14 that oscillation with an animation. It's more clearly. So this application is the one that helps in this. This property is the one that helps in this application in medicine. For example, that is the PTT, that is photothermal therapy. So the idea is that the gold nanoshell with this property of resonance could absorb the near infrared radiation and serve they could be as useful as mediators in PTT because they efficiently converted that absorbed radiation into heat and are also thermally stable at those temperatures. So you can see in the figure 15 an illustration of the process. In figure 16 you can see also the processes and illustration, and in figure this one that appears in green is like the laboratory experiment that did in one of the papers that I read, that the first one is of the cancer cells, the second one the second one from left to right is this cancer cells with those gold nanoshells, and the third one is the process where you have already shined that laser and have destroyed those cancer cells with the gold nanoshells. Now, those were the nanoparticles that I wanted to discuss, but there are some properties or things that we need to study more, understand more, like for example the toxicity and challenges that it has. Quantum dots, for example, it depends on multiple factors, the toxicity, such as for example the quantum size or also the core that the quantum dots has. Major limitation to the clinical application is the toxicity of the core. As I said, they are heavy metals, for example cadmium or selenium. An important problem also is that they target to liver, kidney, and are prone to accumulate in those organs. There are no problems for using this in vitro, but also there is a great barrier for human application for in vivo cancer because of this toxicity. But the good news is that you could study now those limitations and improve those characteristics that of quantum dots, for example, creating an ideal coding that it will be something that has to be biostable or biocompatible, and different things. So I think that we must, scientists must study more those topics. Other thing is that gold nanoshells, they don't have this problem of toxicity because gold is universally recognized the most biological inert of metals, and the silica, that is the core, it has been shown with studies that it's non-toxic. But the challenge here is that there are some problems, like for example, they are hardly digested by enzymes within the body. So this is the barrier, and the challenge will be to develop easily digested and completely cleared after treatment. So those are the discussion of toxicity and the challenges. And finally, my conclusion is that these nanoparticles, for example, gold and quantum dots, have an infinitive potential. They can come here with nanotechnology to improve the several traditional methods, not to substitute, but to improve some methods like new solutions and products to solve healthcare challenges in the future, and also improve the quality of life of the patients. As I discussed during the presentation, quantum dots and gold nanoshells have unique properties like chemical, optical, physical, and could be applied in different medical treatments, like for example PDT or PTT. Also, a lot of animal tested trials have been developed, and they have a great success. Also, imaging techniques are optimized by this nanotechnology, nanoparticles. There's also an economical advantage because they are cheaper than the conventional traditional methods. But there are also not everything is very well established. There are also some challenges. For example, the toxic effect these nanoparticles need to be investigated more. This also implies the sociological and ethical questions. And in clinical trials, they have not been developed, but they are underway. For example, I read that this gold nanoshells application in photothermal therapy, it's in its final stage of the clinical trial. But also there are some of other questions that need to be investigated more by scientists in this multidisciplinary area. Like, for example, what is the largest size of the tumor that a nanoshell can effectively treat, among other questions that are remaining here that need to be investigated more. So that's was my presentation. I don't know if you have any questions that I could answer.
If you have any questions over the chat room, please do give us a message there. Leave us a message there. You have one question? Oh, there's one question. It's not showing up there. Can you read it out loud?
I think it's slightly.
Can you just read it out loud here? A little bit closer. So Peter in Wisconsin wants to know what would be the concentration of nanoparticles needed. In this case, he says that you may have already mentioned, but can you remind him the concentration of gold nanoparticles?
What would be the approximate amount of gold for a single patient?
Oh, the quantity.
Yes,
Exactly.
the amount of
The
gold
concentration.
for one patient. How much it would be?
Well, honestly, I didn't read about that one exactly. I read a lot of here I have the bibliography, but I didn't. It was the papers that I read was about the investigation part, not the clinical trials. So I honestly don't have that fact of how much quantity of gold can you treat. So I apologize because I don't have that fact now.
Do you know how much they use for mice?
No, I don't
No.
remember because no, I don't remember that fact.
Okay. If we don't have any further questions, let's see. Do we have any more questions from the audience?
Mm-hmm.
Or no? If we don't have any more further